At the start of the project, we have a direct drive front-loading washing machine motor. The technician lightly taps with a hammer to separate the outer magnetic casing from the motor shaft. Inside is the permanent magnet rotor and the original stator block with solid copper coils. Using a Makita cordless drill, he removes the bolts securing the stator to the aluminum plate. Now, we need to modify the original wiring circuit to optimize the output voltage. A large gauge bare copper wire is cut and bent into a U-shape using pliers. The technician is fabricating bridges to change the original wiring diagram. Each copper segment is meticulously cut, ensuring a perfect fit with the slots. The bridges are carefully placed into the contacts to connect the phase coils in sequence. Connecting the coils in series helps the machine maximize generated voltage at low speeds. Specialized soldering flux is applied evenly to the joints to increase adhesion. A soldering gun melts the tin, firmly reinforcing the copper electrical bridges on the stator block. 3 wires, yellow, blue, and orange, are soldered directly to the output to conduct alternating current. A multimeter is used to measure resistance, ensuring balanced parameters across the 3 phases. Now the stator needs to be reassembled onto the aluminum plate, aligning the bolts and tightening them with a drill. The permanent magnet rotor is dropped in. The strong magnetic attraction requires skill. The central nut is tightened securely to fix the shaft and set the optimal air gap. The next crucial component is the Sequel 50, a bridge rectifier, rated for 50, a current and 1,200 volts. The 3 AC output wires from the motor will be wired directly to the bridge diode. This component converts the 3-phase alternating current into a smoother direct current. An LED bulb and a cooling fan are wired in parallel to the positive and negative terminals. When test spinning the rotor by hand, mechanical energy is instantly converted into electrical energy for lighting. Hand acceleration generates a current strong enough for the fan to operate stably. Next is the process of fabricating a sturdy support frame for the entire system. A tape measure is used to accurately measure and mark dimensions on the square steel tubing. A chop saw with an abrasive disc cuts the steel segments exactly to the design dimensions. The steel bars are arranged into a rectangular frame and permanently joined using stick welding. Arc welding creates a rigid structure capable of withstanding vibrations during operation. The motor's flange is drilled and screwed directly to the newly fabricated steel frame. An old bicycle freewheel cluster is repurposed to act as the drivetrain for the generator. The bicycle freewheel is aligned with the center of the motor shaft and securely welded in place. The weld around the shaft ensures the ability to withstand high torque without slipping. An old sports bicycle is prepared to serve as the human-powered drivetrain system. An angle grinder is used to cut away the unnecessary rear frame sections of the bicycle. The bicycle frame is then welded directly to the generator motor's support frame. The permanent welding unifies the bicycle and the generator into a single solid unit. The bridge rectifier system is temporarily connected to test the electrical wiring route. The entire metal frame is sprayed with matte black paint to prevent rust and improve aesthetics. Thick rubber pieces are cut into smaller sections to make shock-absorbing pads for the base. Rubber pads are screwed into the four corners of the frame to eliminate vibrations transferring to the floor. The bicycle is reassembled onto the base frame, standing upright and sturdily balanced. The chain is connected from the bicycle's chainring down to the freewheel welded onto the motor shaft. The rectifier assembly is precisely positioned and screwed firmly to the supporting steel frame. When the rider starts pedaling, mechanical force transmitted through the chain spins the rotor, creating a magnetic field that instantly generates electricity for lighting. The generated energy is highly impressive, providing a direct current strong enough to run both the cooling fan and the light bulb in parallel. To optimize power storage, a smart solar charge controller is securely screwed onto a wooden board. The technician carefully strips the copper wires and connects the output voltage from the rectifier directly into the charge controller's input port. A small red painted metal tray is drilled and securely screwed directly underneath to act as a battery holder. A 12-volt telecom dry battery is neatly placed in the tray and safely strapped down with two plastic zip ties. The positive and negative battery terminals are accurately connected to the charger, supplying power to the LCD screen that displays the voltage. Any continuous pedaling motion is now converted into a safe charging current for the storage battery. The load wiring system is connected directly to the controller's output port, ensuring a continuous supply of clean energy. The parameters on the control screen indicate a perfect charging process, with the charging current maintained steadily at over 1 amp. The system operates smoothly, turning leg pedaling power into an excellent backup energy source for the household. Built-in connection ports on the controller allow a data cable to be plugged in to fully charge a mobile phone. The project ends in complete success with the satisfied smile of the person testing this unique power-generating device.